Hello guys, welcome to EE569 CS634 Dynamic Programming and Reinforcement Learning. I am your TA for the course, Muhammad Mahin Mowal, and I'm gonna be this is gonna be your first tutorial on OpenAI Gym. Um, Most of our assignments are gonna be done in OpenAI Gym, so this is just the basic setup and the basic functions that we're going to use throughout the course. So the assignments in this course have been revamped. We're going to be using the Gymnasium now. Previous assignments were in MATLAB. Uh, so we're sort of going to look at the basic setup now and how do you install the OpenAI Gym in this. So the first thing we're gonna set up is a virtual environment, right? Now, for those people who don't know what virtual environments are, virtual environments is basically you want to separate your application code from uh, the rest of your program so that it doesn't so the dependencies don't interfere. We might be using certain packages that might interfere with the rest of your global environment. That's why it is highly recommended to use a virtual environment, right? Uh, I took a poll in the class, in the Slack group, where most of you said that we're comfortable with Python and Jupyter notebooks. I'm going to be using the Jupyter notebook inside VS Code. If you would like to use something else, such as Google Collaboratory or um, Anaconda Jupyter notebooks, that is fine with me as well. But the tutorial is going to be inside VS Code, right? That's what I'm most comfortable with. If you would like to install a Jupyter notebook inside VS Code, you can go to extensions and just write Jupyter, and you can install those extensions, right? Jupyter file is um, named IPYND, and you can install it there, right? So the first thing is setting up a virtual environment. You go select kernel, right? Select Python environments, right? Create a Python environment and virtual environment, right? I'm gonna be using 3.11.4 version, and we have a virtual environment created. It will take some time. Right, so the environment is done. It's still installing IPy kernel, so we're gonna skip ahead. You also notice that I made a requirements file, right? The purpose of this file is basically to give you sort of all the packages you will be needing throughout the course. You might need some more packages. If you need those, you can just install them yourself, right? But this is kind of like a starter pack I can give you, which you can use, right? So the way you would install these uh, requirements is by a command I will show you. First, we have to get this virtual environment done. So we're done with installing, we're done with setting up our virtual environment. Now we're gonna have to install our requirements.txt file. This requirements file I will deliver it to you via Slack or by email. I'll let you know. And what we want to do here is we will say, so we're gonna open a terminal, right? And it will be in the virtual environment. We're gonna say pip install -r requirements .txt. This will install all of your requirements. So now we have our system set up and all the packages are installed. In case you don't know how to get this terminal, you can go to uh, the yeah. So you can go to new terminal and you can get this terminal thing here. Okay, so what we're gonna try and do is run this Jupyter notebook, right? And we're gonna run some code. So let's make this 100. Right. Hold on. Right. So this is the card pull balancing problem. I think the electrical engineering students are more familiar with this problem, right? What you want to do is balance this card pull, and we're going to train using a reinforcement learning algorithm by shifting the um, the thing that's it's balancing on left and right. Um, if it falls, you fail, and then you restart over again, right? Reinforcement learning is primarily self-play or learning by trial and error, right? Uh, you're gonna write those algorithms later on in the course when Dr. Hassan Jalil will be teaching you those, and you're gonna implement those here. But the the purpose of this tutorial is just to understand that it's to set up the environment and understand some of the functions that this code is doing, right? So let's try to go by it line by line, right? So this line imports our gymnasium gym.make, right? So gym.make basically makes an environment uh, in which you can test your reinforcement learning algorithm. I use Cartpole version 1 and added an argument render mode is equal to human. Right? What this argument does is that it renders our Cartpole in a sort of like a window in which we can see the Cartpole. If I eliminate this, then you would not be seeing it anymore. You would just the code would run, but you would not see what the Cartpole actually does. Right. So we're gonna try and do more stuff now. So environment action space dot seed 42, right? By applying a particular seed, we're trying to replicate a particular state of the environment, right? Um, every environment will be somewhat stochastic. There are some deterministic environments in the gymnasium too, but most of them are stochastic. You would not know where the cartwheel is moving, but by putting a seed, uh, it would somewhat it would minimize the randomness, so it would operate on a particular path, right? Obviously, you would not want to do it once it is trained. You would want to do you would want it to run on every seed possible, or most of the seeds, right? So in that sense, you would train it on multiple seeds, right? Uh, then we also want to know what is the action space. So I'm gonna make a new cell. So environment dot action space, right? So what does this mean? Uh, so action space is primarily so action space is primarily the number of possible actions available to your agent. In this example, it would be left and right, right? So um, so if I do environment dot action space, what it gives us is two possibilities. They're discrete possibilities, they're left and they're right. Right? We will also um, want to select those possibilities, left and right. We would want to know what does left mean and what number left means and what number right means. Let's try to understand the rest of the code. So environment dot reset, this line actually resets the environment, right, with the same seed 42, and also returns two interesting things, right? Their variables are observation and information, right? So what are observation and information? Let's look at it closely. So this is the documentation for Gymnasium for the card roll problem. Well, what we're gonna try to do is learn how to read this documentation and understand some of the properties of the environment, right? You can go to Gymnasium documentation and it is in classical control and cardboard. Let's try to read it. Action space, I already told you, there's it's a discrete variable with two possibilities left and right. So you can go here, you can say 0, push card to the left, 1, push card to the right. Right? Let's also look at another variable, observation space. Right? Now what is observation space? So observation space Observation space is the number of possible states the environment can be in, right? Um, so this would basically describe your whole environment by each step. So you can say that the observation space, the three numbers that actually describe the environment. So there's caught position, caught velocity, pole angle, pole angular velocity. Caught position has an x position range from minus 4.8 to 4.8. Caught velocity can go from minus infinity to infinity. Pole angle is minus 0.418 radians to 0.418 radians, and pole angular velocity is also minus infinity. infinity. You can find this observation space here. So minus 3.4 power 0.38. This is, I think, the lowest number Python can get. So you can find the lowest possible value here. What you want to do is, so these are all the possible states that this carpool problem can be in. But also note that the pole angle can only be observed within 12 radians, right? Why? Because after 12 radians, the pole already falls, so it's not very efficient. Like, we don't really need to know uh, after that, because the purpose of the environment is to balance the pole instead of making it fall. Right? Rewards. Rewards are important. Now, what we want to do so as Sir mentioned in class, usually computer science people talk in terms of rewards, and electrical engineering people talk in terms of costs. What we want to do is maximize. So I'm a computer science major, so and OpenAI Gymnasium is primarily written by computer scientists. So we can talk in terms of rewards. Rewards, what we want to do in this particular environment is maximize the amount of rewards, right? The goal would be to keep the pole upright as long as possible, and for every step such taken, you get a +1 reward, right? The starting state is important. You get minus 0. You get assigned a random value between minus 0.5 to 0.5, 0.05. Now this is important. So there are three primary terms: termination, um, the two primary terms, and well, there are two possibilities for the termination state, but the two primary terms you must be introduced to: the termination and truncation, right? So let's talk about those. So there are uh, termination, and there is terminal states are states where the environment would end and you won't be able to do anything afterwards. In the card probe problem, it would be when it goes past 12 radians, minus 12 and plus 12 radians. That's when it would terminate. So truncation is what you need to prevent the environment going on for an infinite number of steps. Why? Because then if let's say you have solved the problem of the pole balancing, and the environment keeps on going on, that would mean infinite reward. So you would want to put a truncated value where you wouldn't want it to go on and on forever, right? So you want to have a finite number of steps. This number of steps in this given in this would be 500, right? So the maximum number of points basically you can get is 500. If the number of steps go beyond 500, you basically lose. So for version 0, it's 200, and for version 1 is 500. We are using version 1. So this is the whole idea behind termination and truncation, right? You can also terminate if the card position is plus minus greater than plus minus 0.24. Um, that's the limits of the environment. Although notice that the observable state is minus 4.5 to 4.8, 4.8 to minus 4.8 to 4.8. But the um, card position can only, but then if you go beyond plus 2.4 or minus 2 or less than minus 2.4, you still end up terminating, right? So this is the idea behind terminal states and uh, truncation, right? Uh, Dr. Hassan Jalil will be indicating, will be explaining that to you in class, but this is kind of a initial explanation of the concepts. Right. So let's understand. So once we've gotten that down, we're gonna understand more of the code, right? We have environment.step, right? So what does environment.step do? Environment.step basically um, gets you to the next step of your current state. So let's say your pole position is in, the first, I think the first state initial observation was this. So pole position was 0.027, pole, I think, yeah, card velocity was this, card pole angle was this, and pole angular velocity was this, right? So with this initial observation, we would want to know that what will be the next step, right? So we will put in a particular action. So we observe something and we put a particular action into the step function that would be left or right, and we observe the next state, right? So this function would return observation, reward, terminated, or truncated, right? And info. You don't need to get into info. For now, let's understand these four terms, right? Observation. Observation is basically the next observation of the next state that you would end up in. Reward is, well, if you get any reward from being in that state. So that would be one. If like we have printed the observation reward terminate truncated. So that will be one in this case. Um, Terminated states. So it's false, and truncated states is also false, right? So this would be true if you went beyond, terminated would be true if you went beyond 4.8 x value, or your angle went beyond 12, plus minus 12 radians. Uh, Truncated would be if you would have done 500 steps and you're still there, and that would be the truncated value. So you can sort of maximize the reward there, right? If terminated or truncated, you would reset the environment and you would get a new observation. So this whole loop runs for like 1,000 iterations. There's no learning in this, but we're only seeing the general ideas behind um, this gymnasium. Um, if you would like to experiment on your own, that I would highly encourage that. We will be sharing this Jupyter notebook with you so you can play around with this. If you want to learn on your own, that would be interesting too. Most of the algorithms we use to solve such environments involve Q learning, deep Q learning. I'm not sure we will be covering deep reinforcement learning, but definitely we'll be covering Q learning. So, and then this environment closes after 1,000 iterations. Hello. So now we're gonna look at a different environment. This is the frozen lake environment. The frozen lake environment is a very different environment compared to the previous one, ball balancing. What you end up doing is basically you start from here, and you wanna end up to your reward, and there are terminal states here. So one, two, three, four. If you drop in any of the puddles, you basically die, right? There are also some other interesting things. So so you have basically four options to choose from every state. As you can see, the action spaces four. You can go left, down, right, and up. Uh, but here's the trick: you can make the environment is intentionally slippery, right? You would in in a sense, if you move right, then there's a 33% chance that you would move right, and a 33% chance you would move up, and a 33% chance you would move down. So basically, whatever direction you move in, there's a 1 by 3 chance that you would move in that direction, and a 1 by 3 chances in each of the perpendicular directions. So let's say you move up, you might move left, or you might move right or up. If you move left, you move left, up, or down. This um, involves this makes the environment inherently stochastic in nature. um, so you wouldn't really know where your person is going, right? um, uh, so there is like what you want is sort of a policy. So what you want is basically for every particular state, I know what I want to do, what is the most optimal action that I can take towards my goal. I have already solved this environment and found the optimal policy. Um, I will not be sharing how I solved that, but that will probably be in one of your assignments. But I will show you that if this is the particular solution to this environment, then how does the solution play out? So So consider this: the action space is basically from zero to is a space of four, where zero means move left, one means move down, two means move right, three means move up. Observation state. So the observation space is basically 15. Why? Because it's actually 16, but the goal doesn't count, so it's 15, right? Um, the starting state is 0. You will be starting right over here. So the reward is very different. So you don't get any rewards for uh, staying in the field. Well, you would only get a reward once you reach the goal. So you only get a +1 there. If you reach any of the hole, there's no reward. If you reach any frozen lake, you get no rewards. Right? You would only get a reward if you reach the goal. Unlike the card pro problem, where you want to maximize the reward by staying upright. In this case, you would only get a reward once you reach the end goal. Okay, let's talk about termination and truncation now. So terminate the terminal state would only happen once you either reach the goal or you get into a pond. The truncated state is interesting. So you don't want to just keep on jumping around in there. Uh, Well, so the length of the each episode would be 100, right? So you can't go on forever. For 4x4 environments, it would end at 100, right? Let's look at this environment. Yeah. So I've initialized environment.gym is slippery true because I want it to be slippery. We'll reset the environment. So here's the thing. I have already found the optimal policy for every observation. So if we have a particular observation, we know what the optimal action is, right? Oh, like if I know I'm in state 0, the optimal action is 0, which is left. If I know I'm in state 4, I know the optimal action is left 0. So we're gonna see how this plays out, right? Uh, I'm gonna reduce some of the iterations, so 10. So this is interesting. What I want to do is while not done, done would be only true when the state is terminated or truncated, right? So while not done, we would keep on running this loop. Um, so what this basically means that we would keep on running until it falls into a pond or it uh, gets to the goal, right? And once it is done, we would uh, sort of. So here's the thing. This is the interesting thing. So if observation is equal to 15, success count would be 1. So what is the success count? The success count is basically the um, so so consider observation number 15 is basically this state, right? This is state 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, because we start here with 0. So if at any point it reaches 15, what would happen is basically I would increase the success count, and it would obviously terminate. Um, so basically, what we're doing here is we're counting the number of successes we would have, and what we're gonna do is find that as a percentage of the we're gonna find is the total number of successes we get, right? And we're gonna do it for 10 observations for now. Why? Because I want to show you how this would actually play out, right? Here we see that for every environment dot step, we do get action and put in an observation. Well, the observation we get. This get action function I've already defined. This is the optimal policy, right? So this is the optimal policy already found by Q-learning. Right? Q-learning is basically the algorithm which is used to find its policy. Now, what we're gonna do is run it actually in real time. So you actually observe how the policy would work on a real environment. So we have this, we're gonna run it. So it's wandering around. We go here. Still didn't find it. It's gonna take some time. 2, 3. You can speed up this part of the video if you like.
So this is interesting. In the previous iteration, we got we landed in a puddle. So it's not like 100% success rate. Right. So we got a success rate of 70%, right? We lost three times and we won 70 times. 7 times out of 10. So the environment is inherently stochastic, and this is kind of like the optimal percentage we get if we run it for any number of iterations. Right? If I run it, let's say for 100 iterations, and I eliminate the random more, so we can run it faster. Hold on, so 100. Okay, but we get a 64%. So in 100 iterations, we got 64 successes. We get 79, 75. The optimal percentage is around 74. If you run it for many iterations, it would reduce the variance and stuff. So this will be the end of your tutorial. I would encourage you to keep exploring the OpenAI gym, and we will be giving you assignments based upon that. I hope this would be an interesting learning experience for you, and it's going to be super fun. Thank you.